not going to go into as much detail as I would if we were in class. I'm not going to cover 3.1, 3.2, and 3.3 as completely as I would. So this is kind of, I gave a little bit of background there, and now I'm going to talk about section 3.3. Just as a general rule, when we've been doing these types of problems, we have seen that very frequently we have some integrating factor we end up with e to some power is the way that things end up going. And so when you see a problem of this type, it's convenient to say, I'm going to guess a solution. I know there should be two solutions, okay, y1 and y2, which I'm going to get at some point. Okay, I know there should be two solutions because it's a second order differential equation. But I'm going to guess that the solution looks like this. Some constant, of course I don't know. And I'm going to guess that it's an exponential, e to some value. And I don't know what that's going to be. I'll say a t, okay? And that c2 e to some bt would be okay too, there. Okay, so what I'm going to do is I'm going to start looking at this. And I'm going to say, okay, if this was y1 is c1 e to the at, then y1 prime would be ac1 e to the at, and y1 double prime would be a squared c1 e to the at. Just taking derivatives of an exponential, right? And I'm going to plug those things in here. That means y double prime is going to become a squared c1 e to the at plus 3 y prime, so that's a c1 e to the at, minus 10 times y, well y is y1, so it's 10 c1 e to the at, and all of that equals 0. Now when I look at this, something that I notice immediately is I've got a c1 in every term. I've got an exponential in every term. Therefore, I can factor those out and be left with this. And now I look at this and I say, well, I'm trying to find what equals 0. Well, if c1 is 0, then the whole problem is just solved by y equals 0. That would be a trivial solution. While that would be true, it would be completely useless for us. So c1 is not going to be 0. E to the at could be equal to 0. Well, no, it couldn't, because the exponential is defined in such a way that it never is 0. It's always positive, right? So what I end up with is that this piece right here must be equal to 0. So I can rewrite this and say, well, I'm not even really concerned about that. This thing needs to be equal to 0. And then I go about factoring this. I say, well, what does that factor into? I've got a and a. Factors of 10. That would be 5 and 2. I need the positive here and the minus here. And I end up with a equals minus 5 or 2. Well, if I go back up here and I look at this, I say, well, that gives me two answers for a. I had said there should be two answers here, where this value is going to be different, but I had just said there'd be an a and a b, but I just found two values for a. What this really tells us is that our y1, again, we don't know the value of the constant yet, nor will we know the value of the constant unless we have some initial conditions, boundary value, whatever. But I can write e to the minus 5t, and that would be my y1. And then I can write y2 equals c, and I'll say c2 again, it could be a different constant, e to the 2t. And I get both those values by just doing this process of making an assumption based on the fact, based on all the things we've done that show us integrating factors are a good way to do this, etc. We've gotten lots of exponentials. So if we guess that this would be an exponential, then we plug it in, very quickly we can get to this point where we see, oh, this looks like, you know, I can get a solution from that. Now, what does this really mean? Well, I said before that if we have a second order derivative, second order differential equation, we get two linearly independent solutions. That means the solution overall for this is the sum of these two. The total solution is c1 e to the minus 5t plus c2 e to the 2t. Well, then that should work in this differential equation. Not just each one independently, but the two of them together should work. So what would I get if I get y double prime of this and y prime of this and plug them in here? I should get the solution, which is 0. So y total prime, well, that would be minus 5c1 e to the minus 5t plus 2c2 e to the 2t. Y double prime, of the total solution, will be 25c1 e to the minus 5t plus 4c2 e to the 2t. And I'm going to plug those things in here. And I plug in here and I get a whole bunch of stuff. So I'm going to start way over here. 25c1 e to the minus 5t plus 4c2 e to the 2t. For this, 3 times this, I get minus 15 e to the minus 15 c1 e to the minus 5t. And 3 times this is plus 6 c2 e to the 2t. Of course, I'm running out of space, and I knew that I would. It's very limited board space here. Minus 10 times y. We said y is this whole thing. So 10 times that, I get minus 10 c1 e to the minus 5t. And minus 10 times that, I get minus 10 c2 e to the 2t. And all of that is supposed to equal 0. And we look at this and say, well, all that's supposed to equal 0. A lot of non-zero stuff. Look here. We got 25, minus 15, minus 10 of the stuff that's the minus 5t. Looks a lot like 0 to me. 25 minus 15 minus 10. And I've got 4, 6, and minus 10 here, which also is 0. So it shows us that once we get these two linearly independent solutions, we can show that they work together, they work independently, doesn't matter. And the process by which we got those was to just make this assumption and go from there. Doesn't always work, because of course not all things are factorable, but if we can factor them, then that's going to be a good way to get a solution.